And off we go. Okay, so guys, from having done a review of chapter 16 and 17, guys, no surprise, this entire unit, our last big unit, is acids and bases, and then chapter 17 is how this relates to equilibria. And guys, we've already looked over the calendar. We have a general sense of how this is all going to lay out, how it's going to unfold. But guys, the bottom line is what we want to accomplish today is gather around the things. Thank you. Did you get done? Yeah. Did you seriously? Oh my gosh, you're a hero. Thank you. Yeah, and do keep me in the loop about the scholarship thing. Yeah, I'm super excited. Okay, thank you, Eleanor. Have a good weekend. So, guys, what we want to do is we want to gather together around the things that collectively we already know about acids and bases. Then, guys, we're going to set the stage a little bit for where we're headed with this. And once we've sort of gathered around a foundation, we're just going to call it a day. This is going to be pretty mellow. But, guys, we do need to at least build a foundation. So, guys, here's what I want you to do. With the person next to you in the next, 90 seconds, guys, brain dump everything that you know, whether it was from last year or other classes or the chapter reviews. Guys, brain dump everything you know about acids and bases. Go. Guys, you got about 10 more seconds. Oh, what a mess. Weak. Yep. All right, guys, let's pull this together. I love that none of you ran out of material. That's pretty great. But guys, one thing that I didn't hear a lot of you talking about that we need to come back to. So guys, remember August? Me neither. No, I know, right? But guys, over the summer and when you got back to school in August, you took a quiz, a test, over and over and over again until you finally got a 90% on it. And one of the things on that test was the strong acids and strong bases. Yeah? Okay, guys, we've used those at some level throughout the year. But guys, now is when those really come to bear. And so, guys, one of the things that you're going to want to do, and this isn't in your notes, maybe you could make this a thought to self next to the title slide. Guys, you need to refamiliarize yourselves with the strong acids and bases. And so, Elijah, I'm not in any way calling you out, but I love that he asked, he's like, hey, what about vinegar, which is acetic acid? Isn't that a strong acid? And the answer is no. How do I know it's not one of the strong...
All health science students, please go to Ms. Yakota's class.
Guys, how do I know that vinegar is not a strong acid? Because it's not one of the 7. Guys, there are 7 strong acids, and that's it. You memorize them. So, guys, when we talk about strong and weak acids, we do it by exclusion. If it's not one of the 7, it's not a strong acid. That's why we need to go back and refamiliarize ourselves. Then, guys, while we're at it, let's do a really quick review of strong bases. You ready? Follow the laser. Guys, the strong bases are all salts that contain hydroxide. But specifically, it is the group 1 hydroxides, not including francium because that's super radioactive. And then it's the group 2 hydroxides below calcium. So guys, I like to remember the horizontal line from the transition metals. So it's group 1, not francium, group 2 below the saddle, calcium, strontium, and barium hydroxides. But guys, say it again, not radium because it's also very radioactive, so we don't count it. But guys, let me give you a little flavor for a deep thought. You ready? And this is great review for the AP test. Don't be passive. Guys, aluminum hydroxide, is it a strong base? No, but you know what? It's a really, really good base. Guys, aluminum hydroxide is better at being a base than any of the strong bases. How can that be? It comes back to something that we learned, just a second, we learned in the very first unit. Remember when we learned about weak and strong and non-electrolytes? What does a non-electrolyte do in water? Nothing, it doesn't dissolve. What does a strong electrolyte do? Dissolves completely, and then a weak electrolyte reaches equilibrium. So guys, aluminum hydroxide is an awesome base. It's just not a strong base because it doesn't dissolve in water. Do you see the difference? No. Thank you. Actually, I apologize. You know what? You're right. Let's go back. What is thank you. Guys, I was thinking to pull this together in this way. We need to be more careful. Guys, non-electrolytes, we said that wrong. Non-electrolytes, do they dissolve in water? They do, but they don't ionize. Like sugar is a non-electrolyte. Sugar dissolves in water, but thank you, Elizabeth. Sugar dissolves in water, but it doesn't ionize. So non-electrolytes are things like sugar. Sand is just not soluble. So guys, sugar is a non-electrolyte. It dissolves but doesn't break apart. Then the things that completely ionize are the strong electrolytes, and then the things that partly ionize, they reach equilibrium. Those are the weak electrolytes. So guys, again, these completely break the hydroxides, and these completely break apart in water. You guys okay with that? Okay. All right. So guys, here's how far we're going to get today. I heard you guys talking about pH. I heard you guys talking about, holy buckets, hydronium ion. I heard you guys, someone was brave enough to say the word conjugate. Well done. Guys, that's where we're going to get today. We are going to talk about definitions for acids and bases. We are going to talk about hydronium ion. We're going to talk about what conjugates are. This is all review from last year, and then we're going to stop. This is going to take like 10 minutes, 7 minutes. You guys ready? Okay. So guys, first of all, this, and you've got the notes. Guys, you need to know 2 different functional definitions for acids and bases. The first one, oh, my screen is frozen. Guys, the first one is the Arrhenius definition. Guys, I'm sorry the slides printed so small. I probably should have done 2 slides per page. But frankly, what you're reading on that paper is the way Lindsay writes anyway, and so we're just fine. But guys, I added this morning to maybe help you better understand this. There's the Arrhenius and the Bronsted-Lowry definition for acids and bases. Guys, a good way to think about it is this. Arrhenius is focused on what they do to water. You'll notice that is not in your notes. You may want to add it, but it's a good way to keep these straight. Guys, in the Arrhenius definition for acids and bases, forgive me, it's based upon It's based upon what these do to water. So guys, acids are things that increase the concentration of hydrogen ion in water. Then guys, bases are things that increase the concentration of hydroxide ion in water. So guys, let's talk about this through the lens of strong acids and bases. I don't expect you to be able to do this, but really quickly, guys, HI, HBr, HCl, HNO3, H2SO4, HClO3, and HClO4 are all of our strong acids. How'd they do? Hey, I have them memorized. You should too. But guys, what do all 7 of those things have in common? They all have hydrogens. And when they go into water, they give away their hydrogens. By the way, where do those hydrogens go? To the water. And what does that form? Hydronium ion. We'll talk later. It's coming on the next slide. But guys, this is the Arrhenius definition. Acids contain hydrogens. The hydrogens go to water. They form hydronium ion. Guys, it's all about what they do to water. So what about bases? Well, guys, we've got the hydroxide salts of the group 1s and the heavy group 2s. They all have hydroxide. That hydroxide goes into water and it increases the concentration of the hydroxide. Is that okay? Okay. So, guys, then we have the Bronsted-Lowry definition. This is coming at you again based on what they do to each other. This is based on what they do to each other. So in this definition, acids donate protons. And bases accept protons. But guys, here's the $10,000 question. For our purposes, this giving and taking of hydrogens we should say that. Do you guys understand that hydrogen ions and protons are the same? Maybe would it be helpful to do this? That hydrogen ions are protons? So guys, for our purposes, the acid-base chemistry that we're going to be doing is going to be in water. Now guys, here's where we need to stop and think. This is going to be one of the things that if you don't comprehend this unit is going to get really weird. So guys, try this analogy on for size. When you were a little kid, you played on a playground, right? When you're out on a playground, you are playing with your friends on the playground. Does that make sense? But you would never say, when I was a little kid, I played with the playground, right? The difference is this. As a child, a playground was the place where play happened as you were playing with something else, somebody else. But you never considered the playground to be a part of the play. Do you know what I'm saying? Guys, that's the difference between aqueous chemistry and acid-base chemistry. Go back to our very first unit when we did aqueous chemistry. Do you remember when we talked about spectator ions? Do you remember when we talked about net ionic equations? Do you remember that? Why did the water never show up in any of those equations? Even more than a spectator, because spectators, guys, were things that didn't do any. Nitrate's always a spectator. Acetate's always a spectator. Why was the water never in the chemistry? It wasn't a part of the reaction. Guys, in those settings, water was simply the solvent that broke the ions apart, and then it let the ions play together. The water was the playground. Well, guys, in acid-base chemistry, water is a participant in the game. Here's why. Guys, water is H2O, yeah? But we can also write it like this. Water can also be thought of as HOH. What does the H make it? An acid. What does the OH make it? And guys, that's one of the things, we're not going to dig deep into this yet, but guys, at some level, you need to start to internalize the idea that in acid-base chemistry, the water is not like a playground. It is not simply a place where things happen. It's a part of the game. And we're going to talk about that as we move through the rest of the year. But guys, keep that in mind. So with that said, guys, maybe you draw this arrow. Do you see that the Arrhenius and the Bronsted-Lowry definitions of acids are the same? Because in the Arrhenius definition, acids give away hydrogen ions. In the Bronsted-Lowry definition, acids give away protons. But hydrogen ions are protons. And guys, for our chemistry, the acid-base reactions we're going to do is in water. That changes as you get deeper into college. But guys, in here, all of our acid-base chemistry is going to happen in water, and consequently, those definitions are the same. Is that okay? But then, guys, this definition is different. Because in the Bronsted-Lowry lens, it's not about bringing OH. It's about taking in hydrogens. And guys, you're going to find out as we move into this on Tuesday, those are kind of the same when it happens in water, but we'll talk about that more later. Do these sit okay with you? Questions there? And guys, believe me, I know this is a little sketch. I'm just planting seeds with you that we're going to allow to mature over the next few days. So if you're going, wait, I don't quite see this, unless you're just totally blown out of the water right now, I promise it'll come together. We okay? Okay. So then, guys, moving along into this a little deeper, if this will let me click, which it won't. Just a second. So, guys, just bringing this full circle. For the majority of our study, guys, we are going to look at acids and bases through the Bronsted-Lowry lens. So what we're going to do now is we are going to look at what these free protons do. So guys, again, Bronsted-Lowry definition says that acids give away protons. The question is, where do they go? Guys, do we need to talk about this anymore? So Bronsted-Lowry definition. Acids give away protons. When acids give away protons, where does that happen? In water. But guys, they are not just simply dissolving into the water. Guys, when an acid goes into water, it gives away protons, and those protons bond to water molecules, and they form hydronium ion. So guys, how does this happen? And the answer is, remember, this is a positive proton. It's kind of like full force hydrogen bonding. Because guys, what happens is this proton is crazy attracted to these unbonded electrons, and it actually forms a covalent bond where they're not sharing electrons, but the water donates both of the electrons into that sigma bond. So it's literally a sigma bond that is fully formed by 2 oxygen electrons, and the hydrogen doesn't bring any electrons. The proton doesn't bring any electrons to the table. Is that okay? Okay, so guys, with that said, do you understand this? When you have an acid solution, there are no hydrogen ions in solution. All of the hydrogen ions that are there hook onto water and form hydronium ion. Guys, that's important. I don't know if you need to jot that down somewhere, but guys, you've got to understand, in a water solution, there is no free-floating hydrogen ion. None. So as a result, guys, we do this. We use them interchangeably. So guys, hydronium ions are actually the things that give acids their properties. Ow, this acid's burning me. No, it's not. It's the hydronium ion that is ripping your cells apart. Hey, look at that acid chew through that baking soda. No, it's not. It's the hydrogen ions. Remember when we wrote the net ionic equations and it was just the protons that are left? Guys, that's the idea. It's the hydronium ion that gives these things their properties. So here's what we do. When we represent the protons that acids give away, sometimes we'll represent them as H3O, because that's actually what's present. But guys, sometimes, just to make the writing easier, sometimes we'll just write down hydrogen ion. But anytime we write down hydrogen ion, we realize that what we're actually talking about is hydronium ion. We just don't include the whole thing because it doesn't make the chemistry any easier. So sometimes it's just easier to get rid of the water and just call them protons. But we really understand that there are no protons in acids. They're always bonded to water. Is that okay? Yeah. Yes, and that's what we're doing next. Yep, that's exactly that. Brilliant. So you ready for this deep thought? And please don't let me blow your mind. But we've been having this conversation for a year and a half now, right? That's an acid. That's a strong acid. That's a weak acid. Those are bases. When we say, ready for this? When we say that something is an acid, what we're actually saying is it's more acidic than water. And when we say something is a base, we mean that it's more basic than water. So water is actually our point of comparison. And so we'll talk about the term in a minute, but water is amphoteric. It's not here. So here, I'll just circle. So it's perfectly an acid and it's perfectly a base, right? So water can do both. So if you've got something that gives hydrogen ions to water, it just means it's more acidic than water, and then the water functions as a base. If you've got something that takes away hydrogens from water, it just means that it's more basic than water, and now water's functioning as the acid. So water will play the role of the other, but really water is our point of reference. So if something's acidic, we just mean more acidic than water. How was that? Is that okay? Guys, again, lots of weird thoughts, but are we okay with hydronium ion? Is that okay? Okay. Then again, guys, this is review. This is where Braden's brain went, which is super awesome. Guys, conjugates. And then we're done. Guys, we're going to answer an interesting question right now. So let's review. When we talk about the Bronsted-Lowry definition of acids and bases, we know that we're tracking protons. Acids give them away, bases take them in. Guys, that then means that when an acid-base reaction takes place, and you can feel free to write this in if you'd like, guys, literally what's happening is a proton goes from the acid to the base. That is what an acid-base reaction does, is it just passes a proton from the acid to the base. But guys, look at what that does. When your acid loses a proton, this thing is now proton deficient. Breathe that in. When an acid loses a proton, it is now proton deficient. Does that make sense? Now, guys, when a base picks up a proton, it is now proton rich. But guess what those things do? They now change roles. Guys, follow the arrows. When an acid loses a proton, it is now proton deficient. So guess what it wants? It wants its proton back. And when it tries to take in protons, it behaves like a base. We call it the conjugate base. And guys, when the base picks up a proton, it's going, hey guys, I got an extra proton. Who wants it? And it tries to give away its proton, and that makes it an acid, but we call it the conjugate acid. So guys, you got to understand, these acids and bases are fully acids. Well, they can be fully acids and they can be fully bases. So how does this work? Well, the acid loses a proton, it becomes the conjugate base. That's what this says. Acid minus a proton becomes the conjugate base. Then guys, the base takes in a proton and it becomes the conjugate acid. So base plus proton becomes the conjugate acid. Is that okay? Yeah. That's the point. And this is where we're going with the question. So this is going to happen in one of two ways. Guys, this is our last big idea, but it's a huge idea. Are you ready? Strong acids. How many of them are there? 7. What makes them strong? And the answer is they only go in one direction. They don't go backwards. They don't reach equilibrium. But now, guys, what about this? All of the other acids that are weak acids, they go forward, but then their conjugate bases do work as bases, and that reaches equilibrium. So, guys, this allows us to ask a really interesting question. How many strong acids are there? 7. What do they all have in common? And guys, the answer is fascinating. Guys, what is it that makes a strong acid a strong acid? Guys, pick your favorite strong acid. Give me one. HCl? Oh, all right. That was easy, but you pulled it out of your hat. So guys, we dump HCl in water. By the way, guys, did you know this? All strong acids are gases in their molecular forms. HCl, HI, HBr, HNO, all H2S, so they're all gases. In their molecular forms, they're gases, and you bubble them through water, and that's what makes them acidic. Guys, they're not acidic in their molecular forms. I mean, they're not corrosive at all. They're molecular. Anyway, so you put them in water, and it does this, and it forms this. So guys, questions for you. Which is our acid, the HCl or the water? How do you know? Because it lost a hydrogen, it lost a proton. Because you come over here and you look and there's the thing without the proton. So guys, if HCl is the acid, what does that make water? The base. And so guys, now we look for the conjugates. So if this is the acid, what is the conjugate base? Is it the Cl or the hydronium? Cl. Guys, this is the conjugate base. Here's the question we now get to answer. Why is HCl a strong acid? And the answer is this, guys. Chloride is a worthless base. It is worthless. Guys, chloride has no stinking ability whatsoever to take protons back in. It's busted. It's done. And guys, because chloride is a worthless base, this reaction does not go in the other direction, and consequently, the HCl fully breaks apart and never goes back. Guess what? That is true for all strong acid conjugates. Guys, HNO3, nitric acid, it reacts with water. What does it form? Hydronium ion and nitrate ion. What do you now know about nitrate's ability to function as a base? Worthless. How do we know that it's worthless? Because this is a strong acid. It doesn't go backwards. But guys, the cause and effect is actually the other way. It doesn't go like this. We don't say that this is worthless because this is strong. The chemistry is actually, this is strong because this is worthless. Does that make sense? So guys, all 7 of the strong acids, all of their conjugate bases are worthless. Now we need to be more politically correct. Guys, we don't use the term worthless. We use the term of negligible strength. We'll talk more about it later. Go ahead.
So those strong acids have to do something with their solubility in water, like hydrochloric acid, hydrochloric acid, hydrochloric acid, were all like a period that like all dissolved in water.
Yeah.
Like nitric acid, boric acid.
So what you're suggesting is it could be more than coincidence that all of the ions that are the worthless conjugate bases and therefore the foundations of the strong acids are also the ions that tend to be highly soluble in water. Those are absolutely related. And so when we get into that day, remember when we were going to talk about the structures of acids? It's even more fast. Let me just give you a hint. Why is it that NO3 is so stable? It's because it's resonance stabilized. It has delocalized pi bonding. That's what actually stabilizes it. That's also true for SO4, kind of. With the ions, it has to do with their complete shells. Sorry, I'm telling you all of it. For the halogens, when they take in that extra electron, they take on the structure of noble gases, which makes them very stable because of their electron structures. So sometimes it's electron structure, sometimes it's resonance stabilization and delocalized pi bonding, but you're absolutely right. Yeah. How you doing, you guys? Yeah.
So if the acid isn't what's corroding stuff, it's the hydronium ion.
Correct.
corroding stuff?
Yes.
Does that mean if you needed a super strong acid, you could just get a bunch of hydronium and right?
Yeah, but the hydronium has to come from somewhere.
Yeah.
Right? If you can't just like grab protons and throw them at water and make hydronium ion. You have to introduce those protons from somewhere. And the place that we introduce those protons from are acids, right? But here's the place where you run into trouble. Saturation. So you can't just infinitely bubble HCl through water and it's just going to keep taking up the hydrogens. Eventually the solution becomes saturated and at that point you're done. And that's where we get our concentrated acids. So like HCl saturates at 12 molar. So my stock bottle of HCl is 12 molar. Sulfuric acid saturates at 18 molar. So there's a limit to how concentrated these can be based on their solubilities. Is that okay? Go ahead.
You're like volatile or HCl, are there still like pure H2O goes in there?
Oh, absolutely. Yeah, and that's actually one of the places we're going to go is we're going to start doing those calculations. Yeah, so the vast majority of the water molecules, even in saturated HCl, are still water molecules. Yeah, no, it doesn't saturate because you're out of water to take in hydrogens. Yeah, no. You guys okay? One more thing to do and we're done. Guys, what about this? CH3. Elijah, this was the thing you mentioned. So this is the chemical formula for vinegar. Our acid is the acetic acid. This is our acidic proton. Guys, that's a term you will get familiar with. This is what is called the acidic hydrogen or the acidic proton. These are not acidic. It's the last one that is acidic. We'll talk about why when we talk about acid structures. But guys, the bottom line is this. I need to write this smaller. Like so. What's our conjugate base? Is it the hydronium ion or the acetate? It's the acetate. But guys, acetate is not a base of negligible strength. It is not worthless. Guys, as a matter of fact, acetate is a pretty good base. And so what happens is this acetate ion goes, hey, yo, hydronium ion, sorry, I think I'm going to take that proton back. And when that happens, the acetate grabs hydrogens from the hydronium and it drives this to equilibrium. So guys, what is it that makes a strong acid strong? Its conjugate base is worthless. What is it that makes a weak acid weak? Its conjugate base actually has some strength. And here's what you're going to find out. The stronger the acid is, the weaker its conjugate base is. And guess what we get to do in this unit? We get to quantify those strengths. How do we do that? Kc values. Kc is products divided by reactants, right? So Kc is products divided by reactants, but now our products are the conjugates and our reactants are the original acid and base. And so guys, we are going to quantify, like we can quantify the strength of acetic acid. The stronger it is, the more product we'll have, the less reactant we'll have, and the Kc value will go up. The weaker a weak acid is, the more of it stays as reactant and the lower the Kc value is. Guess what we're going to do? Guys, these are actually what are called Ka values. They are simply Kc values when your weak thing is an acid. We're done. Things you want to talk about? You okay? Good? Turner, are you good? Are you just itching? Are we good? Okay. So guys, that's it.